tell you that if you don't know anything about this turbulence, it's better to use SST model in every software. NX, ANSYS, SolidWorks, flow simulation. SST, the best way for mostly tasks. So we say without thinking about it, SST model for turbulence, and this is enough for good simulation. So then you are sure you will get really good results. So SST model, and it was all applied. Yes, program know now diesel, turbulence model SST, and use properties what we define. So okay, and now the most difficult part. The most difficult part is this expression. Problem is, it's like now programming now. So, for example, if I want to do moving with these beautiful videos, from the beginning I showed you some videos with moving. It's everything works with really small programs. We need to define like programs, what is moving, differential equation, everything we need to define, and also simple things like pressure inlet, pressure outlet we have to define in ANSYS. So what we have to do, we have to repeat these things. So it's nothing to learn. It's only you need to know how it works. So if you do it once, then you can copy paste it later. So for example, to find the pressure, I need to write in the program like small equation, like in programming. Yes. For example, if I want to know how much is pressure, I have to say area of air per inlet. So it's pressure in phase inlet. If I want to say how much is force, for example, yes, I have to say this area into x body multiplied with 2. So if I want to find flow, I have to say mass flow and so on. So it's what I have to say to find something. Yes, it's nothing to thinking about it. It's only you have to know.
Do we have to insert them?
What?
Do we have to insert the expressions or no?
Yes, we need to insert now manual all expression once, and then you can copy paste it later. So, but now you need to go to expression. Everybody, please. Expression, right mouse button, insert expression, and only with expression it works. So we cannot see pressure without it. So we cannot calculate everything without it. So we can calculate nothing without it. We have to define this expression. For example, Dichte in German is density. You can write density or Dichte. I am doing now like in lectures, and here I have to write my density. I have to repeat this file, 815.3. So 815.3. If you are doing mistake, you will see program tell you that you did mistake. It's everything, no problem. Kilogram divide meter in the power of 3. Apply. Then we have Dichte. And then I have to do other expressions, all other expressions. Okay, maybe I need to do it small, then I will see all expressions. Yes, we need to repeat it. So, huh? I have also to repeat it. Yes, so I try to repeat it. It's easy way. So, okay, Druk is pressure. Yes, you can write pressure name. But pressure, I think you cannot write. Yes. Like pressure mile, or like this one. So new expression is Druck in German, and I say 2 bar. Yes, I calculate 2 bar or 1 bar. Okay, 2 bar. Okay, we will do 2 bar. In your practical work, you will see not 2 bar. This was my idea for this lecture, but I think it's not. We need a lot of time. You have, for example, 0.3, 0.4. Why we see today? was my idea, but it's not so easy maybe for the beginning. Okay, 2 bar, we will see results, what's happened. 2 bar pressure, apply. Okay, then we need to define all these points. For example, pressure inlet static expression called the Druk inlet ST. Then I say, okay, how I can quickly write these words, area aware and so on. It's also easy if you push right mouse button, then you have here functions that you can to use. Oh, moment. Oh, no. You will see here function. Yes, if you push right mouse button, function local base, then you will see functions that you can use in ANSYS. And here you can find this area aware. So then you will not do the mistake. Area aware from pair base static pressure, and in which phase is inlet. So inlet apply. So then we need to control total pressure. Same story, insert expression. Druk inlet total.
The side of there are edges. There's a
P is pressure. So internal parameter pressure.
We don't need to define it.
Yes, you don't need to define. So total pressure is formal. Yes, static pressure plus density multiplied with velocity quadrat divide 2. So total pressure is with velocity, with dynamic part. So static pressure is 2 bar. What we define in reality is total pressure. So, okay, and Druk inlet total is same equation, area A, and you understand? Yes, it's like middle point of pressure in the phase. So area aware. Or for example, area int, it means integral of pressure. Yes, so it means to find force. It's like yes, it's phase multiplied with pressure is force. So, but it's not important. So we need to repeat it, and always in every simulation we need to repeat it. So. Inlet, or we can import it. It's not important always to repeat it. Manual, we can import also this text file. Okay, then to find force, and we need it always force, we need to say force body is again area, what's happened? Area int x, area int, and then we have to add x, in which direction? X direction force from the pressure. Static pressure create force, yes. So total pressure is, if we open something with 2 bar is our total pressure. Then we have flow, we have velocity, static pressure is less than total. So, and but static pressure creates force. Why? We have near the wall, we have 0 velocity. Yes, it means we have only static pressure near the wall. So it means static pressure is our force source. And we say P body multiplied with 2. We calculate now symmetry part, and we say multiplied 2 is our force. Then volume inlet. Yes, it's mass. We say volume inlet. How much volume we have, and this is our mass flow. Of course, our inlet and outlet have to be same. Yes, normally we check our simulation also with inlet outlet. Yes, everything what comes in have to go out. So it's one of three important things to say, is your simulation correct or not? So we see today, important that volume inlet same like volume outlet. It's very often not true. Sometimes you will see that it can be 100% different. It means your simulation is wrong. So we have to calculate it. Mass flow inlet multiplicate with 2 and divide density, Dichte. This is our mass flow inlet. We can copy paste it. Then we say insert expression volume outlet.
Sorry?
Yes?
How you found Dichte?
Dichte is my first what I defined. So it means I calculate mass, yeah? But normally our measurement makes volume.
No, I mean for Dichte, the first one. How you put it?
This one,
You just
in properties, same like in your here, in file of your practice work.
Yeah, but you write it or you use.
No, it's like measurement of diesel.
Like
I write it.
In definition, you write it.
Manual. What do you think? Write it. I come to this. It's properties of flow. Diesel, benzene, everything you can find.
Like you found.
No. You need to write this point. And then, of course, you need to write. Yes. And then kilogram divide. Yes, and then apply.
So for this one and this one you write and this you use function.
Yes,
Okay.
with right mouse button. It's not so good, but we need to do it. It works only this way. And this is easy way. Other software Fluent from ANSYS makes much more difficult. So we need to do it like C program, small program in C. We need to install compiler. It's much more difficult to define this pressure inlet. So this is the best way. It's a really easy way in flow simulation. Okay, and the last point was, what was last point? Volume inlet, volume outlet. Okay, you can copy paste, of course. For example, volume. You can say insert expression volume outlet, and then you can change the outlet. And normally, what we measurement, if you do a measurement, we use liter per minute. So, and now it's cubic meter per second. And to recalculate cubic meter per second and liter per minute, we need to multiply it with 60,000. So we say volume outlet in LPM, for example, liter per minute. So, and this is expression. We can use expression what we defined before volume outlet, multiplicate with 60,000. And then this recalculation cubic meter per second to liter per minute. So, and now I don't see mistakes. It means everything is okay. We don't see errors. So you need to do it, and yes. Later it's much more easy. You can make, for example, editing command editor, yes, and then you can make copy paste. It's really easy. Okay, so now we calculate these all things in program. Then we can see this feels like results. So then you get mistake. So diesel, and for example here I can say reference state 40 degrees, then I know, yes, later, if I open this file, I see 40 degrees temperature. So, but it's not important. Program ignores everything. We can write molar mass 1 million and change nothing. So now for normal simulation we need only density and viscosity. So, okay, and now the next step is not so more difficult. We need to say what is inlet, what is outlet, and so on. Okay, how we can do it? Like in lectures, here default domain, right mouse button, insert, boundary. We need to define boundary condition, yes? So, we need to insert boundary.
Yeah, I just write it.
So, we need to insert boundary. Okay, and boundary is of course first inlet. Is our inlet. Boundary have to have same names like this one. Yes. This inlet is this boundary name. Inlet. Yes. So here we say we have boundary inlet and details of boundary. What is inlet? We say like in lectures is total pressure is inlet. So, and total pressure is with right mouse button expression our pressure to bar. Yes? If I change here this point, yes, you see, from point you can write to bar, but it's better to use parameter. We say right mouse button expression druk. And then I define apply. I see it's optical. I have inlet with 2 bar. Huh? No, it's pressure. Okay, we need to say, of course, to program inlet pressure or inlet flow. Yes, we need to say what is inlet, what is outlet. Okay, we are going. And fine, if we do it, then we can start simulation. Yes? It's okay.
This one? Yes. I didn't find this function with the
Yes, but
and it's like a key, right?
this is base pressure. It's name from program. Program result is for pressure. Here we can see, for example, temperature. Yes. It's okay, no errors, it's okay. So now we need to define this boundary. Inlet. You see one problem that you don't forget it. Your life. You will think about it. Your next life about this problem. With 0.3 bar we don't see problem. So we will see problem only with 2 bar pressure. Okay. Apply, and then we define same story, boundary outlet. What is it? Outlet is phase outlet, and boundary condition is static pressure. No. Stop. Normally outlet is opening. So opening means goes to atmosphere. Yes, it can go inside, can go outside. So it's atmosphere pressure. So atmosphere pressure in every software is okay. Opening pressure is 0. So 0 means in every software it's atmosphere pressure. So what this means? Yes, it means I can change it of course, but it's not it's important that you don't change it. So in default ML, you see here reference pressure 1 atmosphere. It means 0 in program, 1 atmosphere in reality. Like by measurement, yes? You also make measurement with, if you make measurement, you will see 0 with 1 atmosphere. Sensor tell you 0 pressure. So 0 means 1 atmosphere. So it means vacuum is 0 atmosphere in reality. It means in program is -1 atmosphere. Yes? It means -1 atmosphere pressure is vacuum. So, okay, we have now 0. It means 1 atmosphere pressure is outlet. Apply. Okay. Then we say, of course, symmetry, boundary symmetry. Or symmetry like in lectures, what I have in lectures, I wrote. Okay, body was next one. Okay, body. Body is where I want to find flow force. Then we say type of body is wall. It's only wall. Apply. It's nothing. We want to use body only for calculation of flow force. And symmetry. So the last point, symmetry. Okay, boundary called sim. And then I say type of boundary is symmetry. Here is nothing to define. Apply, okay. So then we did everything. So we told to program inlet 2 bar or your parameter, you can change all these parameters. Outlet is 0, symmetry, body, and the other way is also wall. So all other ways is wall. We did it, and it was next step, and the last step for simulation. Okay, it's not the last step. We have, what is a good simulation, flow simulation? We have 3 important things we will see now. How we can be sure that simulation correct. So, before we are going to this step, we need to say solver settings. Okay, yes. So, next step is solver settings. It means it's like same story. I calculate system of linear equation with iterative process, yes. Many systems, 300, 100 systems. If I see that my result, for example, left part of system is like right part, then I say it's everything good. So, and here by solver control, I say how many iterations, how many times I need to calculate the system of equation. Yes. Normally we can write here, I don't know, 1 million. It's not important. So we say 300, for example. It means program stopped after 300. Yes. Do we have good mistake error or bad error? It's not important. After 300, program stops automatically, for example. So, but the main reason is simulation good or not is this mistake. Normally, RMS 10.-4, 10 in the power of -4 is good mistake. So we say the program stops after mistake less than 10 in the power of -4 or iteration number 300. Yes. So, but our target is this target. So first thing, our error have to be less than 10 in the power of -4. So we will see now this. And then second problem I will say later, how we can say simulation correct or not. And number 3 is conservation target. This point means we say that program stops, calculation results are good if error less than this one and if our mass balance less than 1%. So mass imbalance means difference between inlet outlet volume have to be less than 1%. So, and then programs tell us simulation is good. So this criterion 1 and 3, but we have applied. We have one criterion more. It's not enough for the correct simulation. So the last point, we need the last point, how we can say simulation correct or not. So our force is calculated with iterative process. So the last criterion tells us all parameters have to be constant. It means, for example, I calculated after 100 iterations, like it's like, okay, the best way to solve the system of linear equations. So this is like this one. Yes, it means my solution calculated, but one day after 20 iterations I have no change, yes, of my solution. It means my solution is constant, and this is the main criterion for the good simulation. Our control parameters have to be constant: force, pressure, flow. So, and to control parameters during simulation, we need to define monitors. So, this is three important things we will see now during calculation. There is three important things in every software, not important ANSYS or other. We need to define these control parameters during calculation. How we can do it? We can do it with monitors. So here ANSYS has a possibility to say output control. This is the last point before we start the simulation. So output control twice, and here we see monitor. Monitor, we can say which parameter we have to see during calculation. So during calculation we can control these parameters. So what we have to control? We have to control, for example, to see results automatically. During calculation we have control force, body, pressure, inlet, for example, and volume. So I create new monitor control, force, body, apply, and this is the last point before we start. So force body, what is it? Force body, we say it's expression, our expression. Right mouse button, expression. And we say force body is our force body. Yes, apply, or not apply, only force body. Then we say we want to control pressure, inlet. Yes, this is also expression. This is pressure inlet, is total pressure we want to control. What we defined, is it correct? And we want to control flow. Normally, always we want to control flow, LPM, liter per minute, expression, outlet in liter per minute. So then we say apply, and these three parameters we will control during calculation. And now I repeat, what is the correct simulation? Yes, very often we see that somebody makes simulation and this simulation is wrong. So simulation is correct only if 3 points together with.
So for the pressure inlet, which option did you select for the pressure inlet?
Yeah, your inlet pressure, Brook inlet total.
Total, okay.
You can use static also.
For the flow LPM?
Is flow in LPM.
Okay.
So your simulation is correct only if 3 points. If 3 points we see. So 3 important things, and many people forget this point we see now that is wrong. First, we have to see that our error less than 10.-4. Second, we have to see that our all control parameter constant. And number 3, we have to see that our mass imbalance less than 1%, for example. So, and now we can start our simulation. We can close now file, close, and then we can start our simulation. Okay, save, solution, right mouse button, edit. And for free we can use 4 cores. If our PC can, we can say 4 cores for free. So here we can choose double precision is better to use always. It's we have so small points like 1 Pascal. What is it? Yes, and we define 2 bar. 2 bar is 200,000. Yes, big point, and we are working with big and small points. Double precision, and here we can say interparallel 4 cores, for example. So, like in lecture, and then we will start our simulation with 4 cores. It's for free. And then I start run, and very interesting flow simulations, like football watching. So always, if you're watching flow simulations, really it's best. It's best what I'm watching all day. It's very interesting, and it's very interesting. Look how it looks. We control always mistake, error. Look, this is error parameters. What we see now. Our target that error is less than 10.-4. This is the limit. We hope that our mistakes, errors goes under this line, 10 in the power -4. This is first thing. Second thing, okay. And what's interesting in ANSYS, we can change something in our properties during calculation. It's very cool. For example, if I see that my mistakes grow up, I can change something during calculation and to see maybe my error goes down. So, okay, this is mistake, yes, error. The first reason 10 in the power -4, so our target. Okay, then user points, here our 3 control parameters. If you push right mouse button, monitor, we can choose, for example, we can show only flow, for example. Apply, this is our flow, actual, yes, with actual iteration, so much is the flow. Our target, second reason, all control parameters have to be constant. So, and number 3 is mass imbalance, yes? You can add new monitor. If you add new monitor, you will see here a lot of information you can watch during calculation. And important is imbalance. You can add everything, apply, and this is your error, yes? No error. This is difference between inlet outlet is 0. With big difficult tasks, you will see here maybe 20%, 100%. Then it's something bad. Okay, this is everything what we have to control. Our hope that these all lines goes under 10.-4. If it happens, then program stops and says results are correct. So, but results are correct only if all 3 points correct. Yes. First, these all lines under 10⁻⁻⁴. Second, all control parameters are constant. For example, flow. If you see force, then force is not constant. Yes. And number 3, imbalance. Okay, imbalance in this task will always 0. It's okay, 0. But force is not constant. Okay, now we have to wait. Yes. It's nothing to do. We have to check, to hope. You can go to drink a coffee. Now it's a small pause you can do. Yes, you have error, mistake. Revin is now. Yeah, something is wrong. Maybe parameters. I think it's maybe parameters. Okay, help you, please. Yes. Help you collect.
How did you see force?
In the unit, you use the points. Yes, use the points. Right mouse button, monitor, or you can add new monitor. Here down.
Okay, so new monitor.
Yes, something wrong. I see.
Ah, okay. Force.
I saw this. Here is 0. Atmosphere. You define Druck in the 2 bar outlet. Then it's nothing. No flow. Now we have atmosphere pressure outside. Yeah? Should we start? Ah, you try to do it. Okay. Yes, it's base pressure. Okay, try to repeat it. Try to repeat it. So you see, yes, how interesting it is. And lines have to be grow up, go down at your home always.